Hello everybody, welcome back to another video, and in this video we'll be looking at the MIT Integration B qualifying exam from the year 2022. So let's look at the first question. First question, we can see immediately we have a case where the numerator is the derivative of the denominator, therefore we will get the natural log of the denominator. But if you want to see that, why that works is you say u is the denominator, which is x plus sine x, therefore du is 1 plus cosine x dx, and 1 plus cosine x dx is exactly what we have here. So we can replace that with our du, and we'll get the integral of du over u, which is the natural log of u, which is the natural log of the denominator, which is x plus sine x. So we'll get the natural log of x plus sine x plus c. We have the time to put the plus c, so let's just put it, even though it's not required. And we can generalize this by saying that the integral of f prime of x over f of x dx is going to be the natural log of f of x, and then plus c. So now let's look at the next question, and the next question is going to be very difficult if you don't know the famous identity, the fact that the inverse tangent of x plus the inverse cotangent of x, which is exactly what we have on our numerator, when you sum those you get pi over 2, which is because they are complementary functions, because cotangent of x is the same as tangent of pi over 2 minus x, and if you take the inverse tangent, you'll get a case where you have x plus, and then, so that's the tangent, and then pi over 2 minus x, which are the angles, and you'll get pi over 2, because the x's cancel. So we can now use that in our numerator here, and we'll get the integral of pi over 2 over x. So we can factor out the pi over 2, and you get pi over 2 times the integral from 1 to root 3 of 1 over x dx. And of course, that's going to be the natural log of x. We have pi over 2 times the natural log of x. And that's going to be evaluated from 1 to root 3. Now, we'll notice that the natural log of 1 is 0. Because e to the 0 is 1. So therefore, we can ignore that term, and all we need to do is plug in root 3. And we get pi over 2 times the natural log of root 3. And we don't need the absolute value because, of course, we're with the positive numbers. And we can simplify this even further by seeing that the natural log of x to the r is the same thing as r times the natural log of x, which is a property that you can actually prove using derivatives and integrals alike. So that is pretty cool. And now you can see this 3 as 3 to the 1/2. Bring the 1/2 power to the power over 2, and you get pi over 4 times the natural log of 3. So that is the answer to question 2, which is pretty cool. And question 3 is actually a really interesting integral that I will save for another video, as it deserves its own video due to the cool properties that the floor and the ceiling have. We can see that this is the ceiling and this is the floor, but the reverse that I just said. This is the floor, this is the ceiling, and yeah. So let's move on to question 4 actually. So question 4, my personal preference is to multiply by the conjugate, because we know the identity. We know that cos squared x minus sine squared x is equal to 1. So now, because of the fact that it's a hyperbola, so now we can do that by multiplying by the conjugate, and as a result of the difference of two squares, you will end up with this expression right here in the denominator, which means that you'll just end up with the numerator, because it's going to be over 1. So now distributing the powers as well, you'll get sine h times cos h, or cos of x. These are always weird to pronounce. And then we have sine squared of x dx. And now we will have to use the definitions of the hyperbolic trig functions, which are to do with the exponentials. So let's just make this a bit smaller here so that we can work on those. So now we'll be left with the integral, and sine x is e to the x minus e to the minus x over 2, and then cos x is e to the, so this is being multiplied by e to the x plus e to the minus x over 2, and then we have to just square this first thing here, because that's sine squared, so we have e to the x minus e to the minus x over 2, that's all squared dx. So now we can first of all see that this 2 multiplied by this 2 is a fourth, so let's factor out the 1/4, and we'll keep it out of the whole integral, and we'll see why that works. And the second thing we notice is that this is a difference of two squares. We have e to the, where a is e to the x and b is e to the minus x. So we have a squared, which is e to the x squared, which is e to the 2x, multiplying the powers, and then subtracting e to the negative x squared, which is negative x times 2, which is e to the negative 2x. And then now we have to add the sine h, or sine x squared, and we can use a minus b squared, the fact that that's a squared minus 2ab plus b squared. So now we get a squared, which is e to the x squared, which is e to the 2x, of course, the multiplicative power property, that of course only works with real numbers in the certain order. And then we have minus 2ab, which is minus 2 times e to the x times e to the minus x, and then we add b squared, which is e to the negative 2x, and then dx. And we can ignore this because this over 2, because we know that a over b whole squared is a squared over b squared, and 2 squared is 4, and we've already factored out the 1/4 over there, which is very nice. So we can start integrating, because we just have a bunch of sums and differences. But before that, let's just simplify one thing. We have 1/4 times the integral of e to the 2x minus e to the minus 2x, and it's good to be careful of the signs here, because we have negative e to the negative something, and then that means that you'll have to get some more negative divisions in the answer. So yeah, we'll have e to the 2x now. And then second thing we notice is that e to the x times e to the minus x, we can add the powers. X minus x is 0, e to the 1 is 0, or e to the 0 is 1, and that means we'll just be left with minus 2, because this and this cancel out, and then we'll have to add e to the negative 2x here, dx. So let's start integrating. We have 1/4 all factored out, and we'll have e to the 2x over 2 because of the reverse train rule. We take a u sub, essentially u is 2x, and then we'll get the same expression but divided by 2. So now we have to subtract e to the negative 2x and ask ourselves, what's the derivative of negative 2x? That's negative 2, so we divide by negative 2, and then we add e to the 2x over 2, that's the same thing, and subtract 2x, that's the integral of negative 2, and then we add e to the negative 2x over negative 2 once again. And now we can actually factor out a 1/8 to make it a bit easier, because we have a lot of divide by 2 terms. We have e to the 2x minus e to the, or actually, because this is a negative here and this is a negative, this becomes a positive. So this becomes a plus e to the negative 2x, and then we add e to the 2x, and to keep this negative 2x the same, you have to multiply by 2, so it's negative 4x, because you're taking an eighth. Now, so then this negative 2 becomes negative e to the negative 2x. So now we can see that this e to the negative 2x and this e to the negative 2x cancel. We have 2 e to the 2x, so we can group those together. So we have 1/8 now, all times 2 e to the 2x minus 4x. And finally, we can distribute this 1/8 to each term here. See that this 2 and this 8 cancel, become a over 4, and this 4 and this 8 become over 2. So you finally get e to the 2x over 4 minus x over 2 plus c. So that is our answer to the next question. So let's move on to question 5 now, which is a very tedious one to work out. So I will most likely work on that problem with the video sped up after in the parts which are pretty self-explanatory, but just some tedious and careful calculations. So what we see here is that we can also multiply by the conjugate, because we have some square roots, and squaring them will make them, will cancel them, which will make it nice to work with. So just so that we have space, let's just get all of this and not actually do that. So let's just bring all of this over there. Okay, fine, we'll bring that integral sign with us as well, but we can just move it back. Let's just get him back like so. Okay, now we have this. So we multiply by the conjugate, so we'll get the integral of x times the square root of x minus 1, and then because it's the conjugate, we have to now add the square root of x plus 1, and squaring the square roots, that will cancel, and you get x minus 1 minus x plus 1. we'll see that this x and this x cancel, and we'll have -1, -1, which is -2, so we can factor out the negative a half, but we have to be careful here because, wait, what's happening? So just to write this down, we have the integral of, and wait, let's just see if that actually is fine. Yeah, except for the fact that we can distribute the negative, we can distribute this negative to the numerator, and we will actually get, we can factor it a 1/2 here, and we'll get 1/2 times the integral of x, and I'll write the square root of x plus 1 as x plus 1 to the 1/2 power, and then now we have to subtract 1/2 because we distributed that, and that yeah, so that works, and we will get -1/2 times the integral of x times the square root uh yeah, wait, I just realized that I made a mistake here. This is multiplying by the conjugate, so this is actually a minus the square root of x plus 1. That's probably why that calculation looked a bit wrong. So this is x plus 1, and now it actually makes sense because this negative multiplied by this negative over here makes it a positive, so that's why we have a plus. We don't have a negative here in this term, so this actually works out nicely now. So we have x now times this term, however, is negative because it does not have a negative in front of it, so that's why this negative is here. So we have now x, and then we have x minus 1 to the 1/2 power. Once again, that's all with respect to x. So now we can actually perform two different substitutions here, where we have some w is equal to x plus 1, therefore dw is equal to dx, which is pretty cool. And we can say that t is equal to x minus 1 because these are separate integrals, so we can have different u substitutions, or different substitutions because it's not a u anymore. Dt is dx. So now we can take them to their respective substitutions. So we have 1/2 times the integral now of, and we can do this mentally because we know that x, if we solve for x in this equation, we subtract one of those sides. So x is w minus 1, and x plus 1 is now w. So we have w minus 1 to the 1/2 power, or you have w minus 1 times w to the 1/2 power. So therefore you can distribute the w to the 1/2 power to the w minus 1 term, and you get w, oh wait, you get w now to the 3/2 minus w to the 1/2 dw, and that is because you have x is now w minus 1, that's times w to the 1/2, so we can distribute this like so, and you will have the same thing, or a similar case here, where we now subtract 1/2 times the integral x is now t plus 1, so we have we actually have t plus 1 times t to the 1/2, so you'll get now t to the 3/2 plus t to the 1/2 dt, and now we can integrate these fairly easily because we just have some power rules to apply. So we have now 1/2 times the expression. Now integrating w to the 3/2 and bringing that back to the x world, we know that we have to add 1 to the power, so we get 2w to the 5/2/5, and substituting w with, bringing it back with x plus 1, you get 2 times x plus 1 to the 5/2/5, and subtract. Now, same thing, we have 2w plus 1 to the 3/2 now over 3, and subtract now 1/2 times t to the, or now t is, what is that, x minus 1, so we have 2x minus 1 to the 5/2 using the power rule, of course, and now we add 2 times t minus 1 to the 3/2/3. And we can see that we have a 2 in every term in the numerator here, so this 2, and this 2 they will cancel. So this 1 will also cancel, and you'll be left with this original expression. However, when you cancel this 2, and this 2, you still have a -1 that you have to distribute over there like so. So what we actually need to do is we see that we finally get x plus 1 to the 5 over 2 over 5 minus x plus, I realize that I put a w, but this is meant to be an x. This is x plus 1 to the 3 over 2 over 3. Subtracting now, hold on, is that even a thing? Wait, that seems a bit, no, that actually works very nicely. We have now subtracting x minus 1 to the 5 over 2 over 5, and subtract finally, and I realize I put a t here once again. I don't know why I did the same thing. This is x minus 1 to the 3 over 2 over 3 plus c. So this should be our answer. And if you were working this out live in the 20 minutes that you have, you would be able to do it much faster without having to explain the steps. So this, I believe, is the correct answer. So let's see the next one. We have the cosine of x plus cosine x. So that is a very interesting one because we have that from 0 to pi. And actually something interesting is if you have that integral as being an indefinite integral, which means that you do not have the bounds 0 and pi, it's actually impossible to calculate with regular functions. You can't have a regular antiderivative of that. And I don't know if you can use special functions or not for those as well. So what we'll actually have to do is we'll have to observe some properties of the function itself. And we can actually do some stuff before that actually, and see, we can use the summation rule for the cosine, which I believe is cosine A cosine B minus sine A sine B. So this evaluates to the integral from 0 to pi of cosine A, which is cosine x, and then cosine B, which is cosine of x, and then minus sine of x times sine of cosine of x dx. And let's see what we can do here. I'm not exactly sure how you would go from here. Let's see. So we have used the sum rule correctly, but where do we go from here? Well, I believe the first thing that we have to see is that when you draw the graph cosine x plus cosine x, it will look something like, and then when you have the bounds 0 to pi, I'm not exactly sure how you draw this. It's going to look something like, what is it? It's going to be like this from 0 to pi. So this is 0, this is, let's say this is pi. And what you'll actually notice is that the areas, this area below the curve is going to be negative, and this area is the exact same because of the fact that it's an even function. So therefore, this will all evaluate to 0. So that is the answer to that question. So now let's look at question 7. And question 7, you may be tempted to do integration by parts already, or set u to be x cubed. And there's actually a very nice technique, which is to set u to be x squared. We'll see that du is now 2x dx, and therefore dx is du by 2x. This is all standard u sub. Now we bring this to the u world. We have x cubed sine of u du by 2x, and let's actually just take out the 1/2 immediately. Du by x, and this x cubed can cancel with this x. You'll be left with x squared. But what is x squared? That is u. So that's the integral of u sine u du. And now we can use a simple integration by parts where we take, and then because we have in the u world, let's just do the di setup. So we have d, we're differentiating u and then integrating sine of u. This will be 1, this is plus minus plus, this is a 0. And integrating sine, we get negative cosine u. Integrating negative cosine, we get negative sine of u. And now multiplying the diagonals, we'll see that we get negative u cosine of u. What is that? Plus sine of u. And this works because 0 times this is just going to be 0. So now we can bring this back to the x world. We have negative x squared cosine of x squared plus sine of x squared, and then plus c. Okay, so I actually just realized that there was actually a 1/2 multiple that is factored out of this entire integral. So what we actually have is we actually have all of this still divided by 2. So that was a bit of a silly mistake there, but you would actually have this entire expression just divided by 2 plus c. So everything we did was correct, but we just have to remember that. But yeah, so now let's look at question 8. Well, we know that x to the power 4 is the same as x squared, and then, so let's just bring this here. We have x squared, and then that's squared. So what we can do is we can actually take a u sub. We say that u is 2x, and this is very nice because the denominator is x, and if, or actually, wait, no, u is x squared, and if the denominator was an x squared, you have to do some scary partial fraction thing. So here we have du is 2x dx, and dx is du by 2x, is just standard stuff. And we see that this x and this x will cancel. We can bring the 1/2 out. So this is equal to 1/2 times the integral of 1 over 1 minus, and we know that this is the same thing as x squared all squared. And x squared is u, so it's 1 over 1 minus u squared du. And there are two ways you can go about this. And if you didn't know the hyperbolic substitution, well, this actually evaluates to this integral, the integral of 1 over 1 minus u squared du, is actually the inverse hyperbolic tangent of u. So this is the inverse hyperbolic, let's just write this, we still have the 1/2, and not forgetting that this time, of u, but u is x squared. So this is going to come to 1/2 times the inverse hyperbolic tangent of x squared plus c. And the second thing, if you didn't know that, would be to use a trig sub, where you set u to be sine theta, and then du will be cosine theta d theta, and then you would have 1 over, so 1 minus sine squared, which is cosine squared, and that du is cosine theta. So then you would have to do some simplification and things. But let's just keep our answer like this. And now let's look at question 9. And the best bet for question 9 is to just treat it as if it were the regular trig functions, because we know that 1 over cosine squared is the same thing as secant squared. 1 over cosine is secant. So we have secant squared, or the hyperbolic secant squared of x, because it remains to be the same. And again, treat it, the best bet, if you are not familiar with hyperbolic functions, just treat this as a regular secant x. And the integral of secant squared x, well, that is just a very well-known antiderivative of a well-known derivative. So we know the integral of secant squared is just tangent, because the derivative of tangent is secant squared. So this case is going to be the hyperbolic tangent of x plus c. Let's see which one looks. Let's look at question 12. So question 12, we are evaluating that from 0 to 1. So let's see what we do there. Okay, so we can first of all write this is the integral from 0 to 1 of 1 minus x to the 1/2 all to the 1/2. But does that even help that much? Let's see, we have what we can do. Oh, well, we can just try a u substitution here and set u to be the inside of the expression. So let's say that now we have, let's just try u sub here. We have u to be the 1 minus the square root of x. Therefore, du, taking the derivative of 1, is just 0. And we have negative 1 over 2 root x. That's just the standard stuff, dx. Therefore, dx is going to be negative 2 root x du. So now we can take this to the u world. We have the integral of from 0 to 1 of the square root of u, which we'll just write as u to the 1/2. And now we have negative 2 root x. But what we can actually do in this u sub to make it a bit nicer, so let's just start this again. We have we can set u to be 1 minus root x. Therefore, u plus 1 squared is equal to x, because, or wait, no, that's completely wrong. It's actually u minus 1 squared is equal to x, because add the square root of x, and then, wait, I made another mistake again. I don't know how I'm failing everything. It's actually 1 minus u squared is equal to this is equal to x. Okay, this is the final thing, should be correct, because add square root of x on both sides, subtract u, square both sides. 1 minus u squared is x, and now we can take dx on both sides. We can use the chain rule now, so we have 1 minus u, and that's just to the power of 1, times the derivative of the inside, which is negative du. So now we can take this to the u world. We have the integral from 0 to 1 of u to the 1/2, and now our dx is 2 minus 2u, or negative, so let's just take this negative out, and we have times 2 minus 2u du. So now we can actually distribute this, and we'll see that we get negative the integral from 0 to 1 of 2 u to the 1/2 minus 2 u to the 3/2 du, and this is quite simple to evaluate here. We have now actually negative 4 u to the 3/2 over 3, and that's evaluated from 0 to 1. And then we add now, because this negative and this negative becomes a positive, so now we have to have 4 u to the 5 over 2 over 5 from 0, or actually, wait, hold on a second, these bounds are different, and in fact we have to see that because u is 1 minus the square root of x, so we have this x is equal to 0 and x is equal to 1. But now with our u, we have u being 1 minus the square root of 0, which is 1 minus 0, which is 1. So we have the integral really now from, what is this? We have u is equal to 1. And now plugging in 1 into 1 minus square root of x, you get 1 minus square root of 1 is 1, 1 minus 1 is 0. So we get integral from 0 to 1 actually. So this is being evaluated from 0 to 1 and then 0 to 1. So now let's do some stuff. We see that this is negative, and then plugging in 0, we can just ignore absolutely everything, because 0 to the 3/2 is 0. 0, anything multiplied by 0 is 0, and 0 of anything is 0. So this is just negative 0, which is also 0. But then we have to subtract, so we still have to keep a negative there. And then plugging in 1. So we have 1 to the 3/2, which is 1, negative 4. So negative 4 over 3. And now we have to add. And this plugging in 0 is going to be the same thing. It's going to be 0. And then you're going to have a minus. So this plus becomes a minus. And then we'll have 4. What is happening here? We have 4 over 5, and this is 4 over 3 minus 4 over 5. Get a common denominator here. You get 20 over 15 minus 12 over 20, and this is equal to, wait, what am I saying? This is 12 over 15, and this is equal to 8 over 15. So I'm not sure, I haven't checked this yet, but this should be our answer. Our answer should be 8 over 15. This looks correct to me. Okay, well, let's look at 17, because 17 is a pretty famous one that is actually really easy and really cool to work out. Wait, I'm just trying to look at 17. How would you do 17? You have log times log. Okay, wait, let's just do 17. So what we'll actually do is we'll group the functions that are the reciprocals of each other together. So that means we group sine x to cosecant, cosine to secant, and tan to cotangent. So this becomes the integral of, and then what do we have? We have 1 over 1 plus sine x plus 1 over 1 plus cosecant x. And this is all we need for now. So how do we find this out? Well, we know that they are they're not complementary functions, but they're reciprocals of each other. So this is 1 over 1 plus sine x, wait, what's happening? 1 plus sine x plus 1 over 1 plus 1 over sine x. So let's multiply this term here by sine x on the numerator and denominator, so we're still getting an equivalent fraction. So we have 1 over 1 plus sine x. Now sine x, and now what's 1 times sine x? That's sine x. And what is sine x times 1? That's sine x. And what's sine x over sine x? That's 1. And wait a second, this and this have the same denominator, so let's combine the numerators. We get 1 plus sine x over 1 plus sine x. And what is that going to be? That is going to be 1. So what we actually notice is when we have 1 over 1 plus some x and 1 over 1 plus 1 over x, that's going to be equal to 1. And how many of those do we have? Well, we have 1 and 1 pair. We have cosine and cosecant, and we have tan and cotangent. That's exactly 3. So all we need to is we need to integrate 3 in the x world, and that's going to be 3x plus c. That's interesting. And I think that is going to be the last problem I do here. Just taking a look. I attempted to do question 20 using a Weierstrass substitution, but I got to some complicated partial fractions, so I'm sure there's a better way of looking at that. But this was my rundown of attempting to do, or this is me attempting to do the MIT Integrated B Qualifier exam from the year 2022. So that was it for today's video, and thank you for watching.